Welcome to another physics presentation. When I say another, I'm assuming that we didn't volunteer to go first because that's not our style. And we're going to talk to you about magnetism.
But Matt, what is magnetism? That's a really dumb question, Ben. Who put you in AB Physics C? But let me explain anyways. Wait, two Matts. Who can handle this much magnitude? Shut up! So magnetism is a force exerted by either a Lloydstone or an artificial magnet on materials that have magnetic properties. Yeah, well, of course I knew that. I have magnets on my fridge. I'm not an idiot. Yes, you is. Ouchie! But the force that a magnet exerts is different depending on where on the magnet. Why is that?
To answer your question, Ben, I think we need to go into the field. A magnetic field, that is.
Matt, you're not funny. Your mom thinks I'm funny. No, not you, Matt. The other Matt. I knew two Matts would lead to recurring jokes.
But first, we have a short break. We thought these experiments were really cool, but unfortunately they take intensive care and time to set up, so we thought we should show them to you. Hold on 1 second, technical difficulties, and here we go. And now, back to our regularly scheduled presentation.
Magnetic fields are similar to gravitational fields in that they are all around a particular object and affect nearby objects. However, they differ from gravitational fields in that they attract and repel objects and are strongest at the poles. Alright, that makes sense, but what causes those poles to exist?
Another excellent question, Ben. We need to go down to a molecular level to explain that.
Blast again! They switched on me again. It's almost as if the author of the script has only one joke. That's exactly what's going on! I'll see you again!
Magnets have poles because they have a more positively charged end and a more negatively charged end due to the distribution of electrons at the molecular level. The end that has more electrons is more negatively charged and vice versa.
Wow, that's the first time that I learned something new in this presentation.
Seriously? I mean, when I wrote this script, I was basically recycling what I learned in 3rd grade science class. How'd you miss that? Ouchie a 3rd time.
Wait! I got slapped the first 2 times!
Moving on. And now it's time for another video break. You may have seen the levitating top in the last one, but we're going to show it to you again because this experiment makes use of a special electromagnet, one that we don't have access to at this school, but was just too cool to miss. Notice how the object is unaffected by the physical separation between itself and the magnet. And technical difficulties again.
Hey, I heard that you can create a temporary magnet by running electricity through iron, cobalt, or nickel. How does that work? Okay, that is definitely a third grade question. But that works because running electricity to run through a polarized element causes all the electrons to line up on the same side of the different atoms, creating a north and south pole.
How and why we decided to bend all these magnets into horseshoes, that I don't know.
Oh, okay, so it's like the components for a magnet are already present and the electricity causes the individual magnetic atoms to all face in the same direction.
That's actually right. Good job, Ben, I guess.
And that's what the equation for the magnetic pole of an electromagnet, which is called the Beal-Savart law. Aiden, you can look at that if you want to, but it's gibberish to the rest of us. The important thing to know is that the force of one magnetic object on another is inversely proportional to the distance between them.
Oh. Well, crap. This is going